everyone's doing great. Today we are looking at something different. We're going to look at a solution, or should I say multiple solutions, for day 6 of Advent of Code 2023. So this problem came out today. It was one of the easier problems. At least I found it easier than the day 1 problem. And this problem is interesting from the perspective of having multiple different ways to come up to the correct solution. So essentially a time and distance value, and for a given time value there could be multiple distance values depending upon the statement here. For example, the time value of 7 can have distance values of 6, 10, 12, 12, 10, 6, and zeros as well. So the problem asks us to find is all these distances which are greater than the distance value, the time that you hold the button, which you could say x, and then the rest of the time, so the boat moves at x speed. So if you hold it for 1 millisecond, then it'll move at 1 millimeter per millisecond. For the rest of the time, that's 6 milliseconds because it's 7 in total. And so the distance traveled will be 6 and so on. And the next one is, it's 1 times 6, and then 2 times 5, 3 times 4, 4 times 3, and so on. Yeah, and how many of those values are greater than the distance value. Okay, so let's look at 3 different ways of solving this problem. So let's look at the first technique, the brute force technique. This is the technique I employed. It's very easy to come up with. So given a time and a distance value, we essentially look at all distances which are given by the expression x times t minus x for x in the range of 1 to t minus 1, and we take the count of all the distances which are greater than the given distance. And so this is a one-liner in Rust. So essentially the range from 1 to t maps to the function x times t minus x, and then we filter on all x which are greater than the given distance, and then take account of that. And that's basically the answer. Runs quite fast for both part 1 and part 2, so no other optimizations need to be done. But we shall see at a couple of methods by which we can arrive at the answer much faster. All right, so let's look at the second technique, it's binary search. So we observe that the equation x times t minus x equals d is a quadratic equation in x, and hence it is monotonic in the interval 0 to t by 2. This is essentially because a quadratic equation traces out a parabola, and the middle of the parabola is t by 2 here. And so from 0 to t by 2, the function is strictly increasing. And we very well know that for any monotonic function, we can use binary search. This is my implementation of binary search. We set a low and a high. The low is at 0, the high is at t by 2. And every time we search, we cut the range by half. So we figure out the mid. And if the mid value is less than our distance, then we set low to mid. Otherwise, if it's greater than distance, then we set high to mid. We continue until low and high approach very close to each other. There is a little adjustment that we need to do in the lines bottom. This is because our domain is discrete, so t and d are integers, whereas the binary search was being run on real numbers, and so you need to do this adjustment. I leave it as an exercise for you to figure out why this works. Right, and the last solution is the analytic solution. This is very interesting because not many programming problems have an analytic solution, and this is one of those rare problems which do, again, we observe that the equation is a quadratic equation, and hence its shape is a parabola. And there are two roots to this equation. What we seek are all the values of y given by x times t minus x minus d that are greater than 0. What that means is we need to find the distance between the two roots, and that is essentially our answer. Here you see the parabola, which is the plot of the equation, and the two roots x1 and x2. So all the values on the red plot, which are above the x-axis, are all the points or all the values of x for which the value of y is greater than d. So that's our answer, which is given by the floor of x2. Why the floor? Because the value should be strictly greater than d. And we're looking at a real number plot. For x1, we have the ceiling, so it has to be on the right side. And the difference, accounting for the range, and that's essentially our answer. So this is the Rust code for the analytic solution. We do some adjustments for when the ceiling and the floor equals the actual value, in which case we need to make some adjustments, but other than that, that is basically the analytic solution to this problem. The runtimes are not very important because all three are essentially fine. So the brute force approach goes into the milliseconds, and the binary search returns in a few nanoseconds. What I did was I ran both parts multiple times. The top numbers are for part 1, the bottom numbers are for part 2. And the analytic solution here, it doesn't appear because it's nearly instantaneous, so it's essentially 0. It does not appear on the plot. And that was it. If you haven't subscribed, please subscribe. If you like this video, press the like button, leave a comment. Your likes and comments are always very encouraging. See you around. Until next time, cheers.